So in this example, we are going to work to find a solution to this expression, this differential equation, x cubed plus y cubed dx minus 3y squared x dy equals to 0. And as the title suggests, we first want to test this equation to see if it is homogeneous, and if so, what degree that it is. So we can test for that as follows. Uh, to test for homogeneous properties, we simply apply the test of f x of y, except we replace it with lambda x lambda y. And so when we do that with our expression, we get the following, and here we just replaced the x's and y's with lambda x's and lambda y's. And when we reduce this, we see that we can factor out a lambda cubed. And ultimately, when we do, we see that this really just works out to be lambda cubed times the original fxy. So that tells us then that this equation is homogeneous, and because the power of lambda is 3, the degree is 3. So this is our test for that, and we can see that this is what we're dealing with. So since this is a homogeneous equation of degree 3, we now will use the standard transformations when dealing with these types of equations. And that is, we'll substitute Vx for y. And so using the chain rule and taking the derivative there for dy, we will put in v dx plus x dv. So when we do that, that transforms our original equation to this equation here, and we can do some reducing to this, which gets us to this expression here, 1 minus 2v cubed dx minus 3v squared x dv equals to 0. So now, starting with this equation, we recall that if we have an equation of this form, f some function of x times function of v dx times some function of x times some function of v dv. This gets us back to the separation of variables. So by inspection, we can then define an integrating factor, which is typically 1 over f2x times g2v, which can, if we do that, it can reduce the original equation to this, which this is the whole goal of separation of variables, to have one term all in x, one term all in v equal to 0, and then we usually can apply some integration tactics or strategies to that. So for this transformed equation, remember this isn't our original equation, we transformed it. We can now assign these factors. So our f2 of x will just be x, and our g2 of v will be 1 minus 2v cubed. So this would then give us an integrating factor of 1 over x times 1 minus 2v cubed, which when we apply, this will change our original equation to this expression here. And here you see we do have everything in this term in x, and this one everything in v. So this is what we wanted. The variables have been successfully separated. So now, this being the case, we can now integrate directly term by term. So in this case, we just apply the integral, and again for completeness, showing the integral of the 0, which meant we probably integrated a constant, some unknown constant at that point. So by integrating each term, we come up with the following. So dx over x just gives us natural log of x. The integration of this expression gives us 1/2 natural log 1 over 2v cubed. And then, like we said, we have some arbitrary constant here that if we had boundary conditions, we could solve for. So now with this, we can multiply through by 2, and then we can apply some natural log properties to reduce this further. So when we do that, again, combining terms, what we come up with is this final expression. And so this is the general expression, but again, we have to remember this is the solution for the transformed homogeneous equation. We must now transform back to our original variables, which we'll do on the next slide. So we recall that our transformation was that y is equal to vx. So working that backwards, that means that v is equal to y over x. So we need to go back and make that substitution back in our equation, and when we do, we just substitute that directly in, or to clean things up, multiplying through by our x's, we come up with this, which is now our general solution to this original differential equation that we had from the start.